The universe is a stage of cosmic absurdity, where the laws of physics don't just bend, they twist, contort, and sometimes seem to laugh in the face of everything we thought we understood about planetary formation and behavior. For millennia, humanity gazed up at the night sky with nothing but wonder and speculation, constructing elaborate mythologies to explain those distant points of light. We imagined other worlds, certainly, but our imaginations were constrained by the only example we had. Our own solar system, with its orderly arrangement of rocky inner planets and gas giants, orbiting peacefully in the outer reaches. Then came the revolution. In the final years of the 20th century and the opening decades of the 21st, we developed the technology to detect planets orbiting distant stars, exoplanets, as we call them. And what we discovered shattered every comfortable assumption we'd made about how planets should behave. The universe, it turns out, is far stranger, far more creative, and far more willing to break its own rules than we ever dared imagine. Today, we know of thousands upon thousands of exoplanets, each one a unique world with its own story to tell. But among this vast catalog of alien worlds, certain planets stand out not for their similarity to Earth, not for their potential to harbor life, but for their sheer, mind-bending bizarreness. These are worlds that shouldn't exist, according to our models. Planets that defy explanation, cosmic oddities that force us to rewrite the textbooks with each new discovery. Let's begin our journey through the cosmic cabinet of curiosities, with a planet that exists in a state that should be impossible, a world caught between solid and vapor, between existence and dissolution. Imagine a planet so close to its parent star that the very rocks beneath your feet, if you could somehow stand on them, would be boiling, vaporizing, streaming away into space like steam from a kettle. This isn't science fiction. This is Korat 7b, and it represents one of the most extreme environments we've ever detected beyond our solar system. Korat 7b orbits its star at a distance that makes Mercury's orbit look positively spacious. We're talking about a planet that completes its entire year, its full orbit around its sun, in just 20 hours. 20 hours. That's less time than it takes Earth to rotate once on its axis. To put this in perspective, if you were standing on one spot on Korat 7b, you could watch the sun rise and set in a single Earth day with time to spare. But the implications of this proximity go far beyond just a quick year. The temperature on the day side of Korat 7b reaches approximately 4,000 degrees Fahrenheit, hot enough to melt iron, hot enough to vaporize rock itself. And that's exactly what's happening. The surface of this world isn't solid in any conventional sense. Instead, it's a churning, boiling landscape where the ground itself evaporates, where pebbles rain down from the sky, because the rock that vaporized on the day side condenses and falls as precipitation on the cooler night side. Think about that for a moment. On Earth, we have a water cycle. Water evaporates from the oceans, forms clouds, and falls as rain. It's a fundamental part of what makes our planet habitable. Korat 7b has the same kind of cycle, except instead of water, it's rock. Instead of rain clouds, there are clouds of vaporized silicates. Instead of raindrops, you have pebbles, actual fragments of stone falling from the sky, like hail in a thunderstorm. The planet is tidally locked, meaning the same face always points toward its star, just like the moon always shows the same face to Earth. This creates an eternal division between a day side that's hot enough to boil stone and a night side that, while still incredibly hot by Earth standards, is cool enough for some of that vaporized rock to condense and solidify. The result is a perpetual cycle of destruction and renewal, a planet that's literally evaporating away on one side while rebuilding itself on the other. Scientists estimate that Korat 7b is losing mass at a rate of around 10,000 tons per second. That might sound catastrophic, but given the planet's enormous total mass, this process could continue for billions of years. Still, it raises a fascinating question. What will Korat 7b look like in another billion years? Will it be completely evaporated, leaving nothing but a cloud of rock vapor and perhaps a small, dense core? Or will it reach some kind of equilibrium, a balance between the material it loses and the material that recondenses on its surface? The discovery of Korat 7b in 2009 forced astronomers to confront the reality that planets can exist in states we never imagined possible. It was one of the first rocky exoplanets ever discovered, and it immediately became clear that rocky planets in the universe don't all look like Earth, Mars, or Venus. Some of them exist in conditions so extreme that the very concept of a solid surface becomes questionable. But Korat 7b, as bizarre as it is, represents just the beginning of our cosmic catalog of the weird. Because if you think a planet where rocks evaporate is strange, wait until you learn about worlds where the fundamental fabric of space and time behaves in ways that make Einstein's theories seem almost conservative. Let's shift our attention now to a different kind of extreme. Not extreme heat, but extreme density, extreme gravity, extreme everything. Let's talk about planets that orbit not stars, but stellar corpses. Let's talk about pulsar planets. Pulsars are among the strangest objects in the universe. They're the remnants of massive stars that have exploded in supernovae, leaving behind a core so dense that a teaspoon of its material would weigh as much as a mountain on Earth. These neutron stars rotate at incredible speeds, some spinning hundreds of times per second, and they emit beams of radiation from their magnetic poles like cosmic lighthouses. When these beams sweep past Earth, we detect them as regular pulses of radio waves, hence the name pulsar. For decades, astronomers assumed that no planet could possibly survive the cataclysmic supernova explosion that creates a pulsar. The violence of such an event should vaporize any nearby worlds, scattering their atoms across light years of space. But in 1992, astronomers discovered something that defied all expectations. Planets orbiting a pulsar, designated PSR-B 1257 plus 12. These weren't just one or two planets either. There were at least 3 of them, possibly more, orbiting this stellar corpse in relatively stable orbits. The discovery was revolutionary, not just because it proved planets could exist in such extreme environments, but because these were actually the first planets ever confirmed to exist outside our solar system. Think about that. The very first exoplanets humanity ever detected weren't orbiting a normal star like our Sunday. They were orbiting a dead star, a rapidly spinning neutron star that bathes them in lethal radiation with every rotation. The planets around PSRB 1257 plus 12 are subjected to conditions that make Korat 7b look almost cozy by comparison. The radiation environment is so intense that any organic molecules would be instantly destroyed. The gravitational field is so strong that it warps space and time in measurable ways. And the pulsar's rotation creates a magnetic field billions of times stronger than Earth's, strong enough to tear apart atoms and distort the very fabric of electromagnetic fields. What makes these pulsar planets even more mysterious is the question of their origin. Did they form after the supernova, coalescing from the debris of the explosion like a phoenix rising from ashes? Or did they somehow survive the supernova itself, perhaps shielded by distance or by some other mechanism we don't yet understand? Some astronomers have suggested a third possibility, that these planets are the remnants of a companion star that was destroyed by the pulsar, its outer layers stripped away to leave only a dense, planetary mass core. The truth is, we still don't know. Each possibility seems equally unlikely, and equally fascinating. If these planets formed after the supernova, it tells us that planet formation can occur in environments far more chaotic and violent than we ever imagined. If they survived the explosion, it means planets are far more resilient than our models suggest. And if they're the remains of a destroyed star, it opens up an entirely new category of planetary formation that we hadn't even considered. What's particularly intriguing about the PSR-B 1257 plus 12 system is its complexity. These aren't just random chunks of matter orbiting a pulsar, they're arranged in a genuine planetary system with distinct orbital periods and masses. The innermost planet, designated A, is about twice the mass of our moon and orbits the pulsar every 25 days. The next 2 planets, B and C, are roughly 3 to 4 times Earth's mass and orbit every 66 and 98 days respectively. There may even be a 4th planet farther out, though its existence hasn't been definitively confirmed. The precision with which we can measure these orbits is extraordinary, thanks to the pulsar's incredibly regular rotation. Pulsars are like cosmic atomic clocks. Their pulses so regular that we can detect variations in timing caused by the gravitational influence of orbiting planets. This technique, called pulsar timing, allows us to detect planetary masses and orbits with remarkable accuracy, in some cases, more accurately than we can measure planets around normal stars. But living on one of these worlds, if we can even call it living, would be an experience beyond comprehension. The sky would be dominated by the pulsar, a point of intense radiation spinning at dizzying speeds. The pulsar's beam would sweep across the planet multiple times per second, creating a strobe light effect that would make any conventional notion of day and night meaningless. The radiation levels would be so high that any unprotected matter would be torn apart at the molecular level within seconds. And yet, despite these hellish conditions, the planets orbit on, silent witnesses to the death and rebirth of their stellar parent. They represent one of the universe's most profound ironies: worlds born from destruction, existing in conditions that mock the very concept of habitability, yet demonstrating a kind of cosmic persistence that's almost beautiful in its defiance. From the radiation-blasted worlds of pulsar systems, let's journey to another category of cosmic oddity planets that exist in places where our theories say they shouldn't be able to form at all. Let's talk about planets in the middle of binary star systems, worlds that dance between two suns in a gravitational ballet that should tear them apart. Binary stars are incredibly common in the universe, in fact. Most stars exist in binary or multiple star systems rather than as lonely singles like our Sunday. For a long time, astronomers believed that planets couldn't form in binary systems, or at least not in certain orbital configurations. The gravitational chaos created by two stars orbiting each other should disrupt the protoplanetary disk, preventing planets from coalescing. And even if planets did manage to form, their orbits would be unstable, eventually leading to them being ejected from the system or crashing into one of the stars. But the universe, as always, proved us wrong. We've now discovered numerous planets in binary star systems, and some of them orbit in configurations that shouldn't be stable according to our models. One of the most remarkable examples is Kepler-16b, a planet that orbits both stars in a binary system, what astronomers call a circumbinary orbit. Picture this: two stars, one slightly smaller than our Sun, and one much smaller and cooler, orbit each other every 41 days. And around both of them, at a distance of about 65 million miles from their common center of mass, orbits a planet roughly the size of Saturn. This planet experiences a sky with two suns, just like Luke Skywalker's home planet of Tatooine in Star Wars. But unlike the fictional Tatooine, Kepler-16b is a gas giant, a cold world where the temperature never rises above -100 degrees Fahrenheit. The discovery of Kepler-16b in 2011 was groundbreaking, not just because it confirmed that circumbinary planets exist, but because it demonstrated that such planets can maintain stable orbits over long periods. The gravitational dance between the two stars and the planet is incredibly complex, involving what physicists call three-body dynamics, a problem so complicated that it can't be solved with simple equations and requires sophisticated computer simulations to understand. What makes these circumbinary planets even more fascinating is what they tell us about planet formation. For a planet to form in such a system, the protoplanetary disk must have been stable enough, for long enough, to allow dust and gas to accumulate into larger and larger bodies. This suggests that planet formation is a more robust process than we previously thought, capable of occurring even in gravitationally chaotic environments. But Kepler-16b isn't alone. We've now discovered dozens of circumbinary planets, each one adding to our understanding of how planetary systems can form and evolve. Some of these planets orbit their binary stars at distances where the gravitational perturbations should make stable orbits impossible. Yet there they are, defying our predictions and forcing us to refine our theories. Then there are planets in even more extreme binary configurations worlds that orbit just one star in a binary pair, but orbit so close to the other star's gravitational influence that they experience wild variations in their orbital parameters. These planets can have orbits that precess or rotate at rates thousands of times faster than the precession of Mercury's orbit in our solar system, creating conditions that would make navigation and long-term prediction almost impossible. Now, Having explored worlds that orbit dead stars and binary systems, let's venture into an even stranger realm, planets that exist in a state of perpetual twilight. Worlds so distant from their stars that they hover at the very edge of what we can call a planetary system, and worlds that challenge our very definition of what a planet is. Consider the case of rogue planets, or what astronomers sometimes call free-floating planets. These are worlds that don't orbit any star at all. They wander through interstellar space alone, untethered from any solar system, drifting through the cosmic void in eternal darkness. For years, these objects existed only in theory, but we've now detected numerous candidates, and the evidence suggests they might be shockingly common, perhaps even outnumbering stars in our galaxy. How does a planet become a rogue? There are several possibilities, each one telling a different story of cosmic violence. Some rogue planets might have been ejected from their home systems through gravitational interactions with other planets or passing stars. Imagine a young planetary system, still chaotic and unsettled, where planets are migrating inward and outward, their orbits shifting and evolving. In such a system, gravitational encounters between planets can occur, and sometimes these encounters result in one planet gaining enough velocity to escape the star's gravity entirely, shooting off into interstellar space, like a billiard ball struck off the table. Other rogue planets might never have been part of a planetary system at all. They could have formed directly from the collapse of gas clouds, much like stars do, but without gathering enough mass to ignite nuclear fusion in their cores. These objects blur the line between planet and failed star, occupying a gray area in our classification schemes that forces us to question what we mean when we use the word planet. What would it be like on a rogue planet? The darkness would be absolute, broken only by the faint glow of distant stars. Stars so far away that their light provides no warmth, no energy, nothing but a reminder of the vast emptiness surrounding the world. Without a star to provide energy, any atmosphere would freeze and fall to the surface as ice. Oceans, if they ever existed, would be locked beneath thick layers of frozen atmosphere and ice that could be miles deep. But here's where things get interesting. Some rogue planets might not be completely frozen wastelands. If a rogue planet is massive enough, it could retain internal heat from its formation for billions of years. This geothermal heat could create subsurface oceans beneath the frozen surface, environments that might, and this is purely speculative, potentially harbor life. Not life as we know it on Earth's surface, dependent on sunlight and photosynthesis, but life based on chemosynthesis, drawing energy from chemical reactions and geothermal heat, much like the organisms that thrive around hydrothermal vents in Earth's deep oceans. The possibility that rogue planets could harbor life forces us to reconsider our assumptions about where life can exist. We've always assumed that life requires a star, that the warmth and energy from stellar radiation are prerequisites for biology. But if life can exist in the dark oceans of a rogue planet, then the universe might be teeming with biology in places we never thought to look. Worlds drifting in the darkness between the stars, invisible to our telescopes, yet potentially alive. Some estimates suggest there could be billions of rogue planets in our galaxy alone, possibly even trillions. If even a tiny fraction of them harbor subsurface oceans and simple life, the implications would be staggering. Life might not be a rare cosmic accident, confined to a few lucky planets orbiting in the habitable zones of their stars. Instead, it might be a common phenomenon, scattered throughout the galaxy in dark, hidden worlds we're only beginning to discover. From the darkness of rogue planets, let's journey to their polar opposite worlds, so bright, so hot, so intensely irradiated that they glow like coals in a fire. Let's talk about ultra-hot Jupiters, gas giants that orbit so close to their stars that their atmospheres are literally being stripped away. WASP-12b is one of the most extreme examples we've found. This planet orbits its star so closely that its year lasts just 26 hours, and the temperatures on its day side reach nearly 4,600 degrees Fahrenheit, hot enough to vaporize most metals. The planet is so close to its star that it's being tidally distorted, stretched into an egg shape by gravitational forces. But the truly bizarre aspect of WASP-12b is that it's being consumed by its parent star. The extreme heat and gravitational tidal forces are pulling WASP-12b apart, stripping away its atmosphere at a rate of about 6 billion tons per second. That's not a typo, 6 billion tons every second. Material from the planet's atmosphere is flowing onto the star in a process that astronomers call Roche-Lobe overflow, creating a stream of gas that spirals down onto the stellar surface. Scientists estimate that WASP-12b will be completely consumed by its star in about 10 million years, a cosmic blink of an eye. What makes this even more dramatic is that we can actually see the process happening. Observations have detected atoms from the planet's atmosphere in the star's spectrum, and we've mapped the stream of material flowing from planet to star. It's one of the most direct observations we have of a planet in the process of being destroyed, a world in its death throes, bleeding its substance into the furnace of its parent star. But WASP-12b represents just one example of a whole class of planets called hot Jupiter's gas giants that orbit extremely close to their stars. These planets shouldn't exist according to our original theories of planet formation. Gas giants should form far from their stars, in the cold outer regions of protoplanetary disks where ice and volatile compounds can condense. That's where Jupiter and Saturn formed in our solar system, and for a long time, we assumed that was the only place where gas giants could form. The discovery of hot Jupiters in the 1990s forced a complete revolution in our understanding of planetary system dynamics. These planets, we now believe, did form in the outer regions of their systems, but then migrated inward, spiraling closer and closer to their stars through interactions with the protoplanetary disk or through gravitational encounters with other planets. This migration can be smooth and gradual, or it can be violent and chaotic, potentially ejecting other planets from the system in the process. Some hot Jupiters have orbits that are not just close, but retrograde. They orbit their stars in the opposite direction from the star's rotation. This is completely contrary to what we see in our solar system, where all the major planets orbit the Sun in the same direction that the Sun rotates. These retrograde orbits are evidence of violent gravitational encounters in the planet's past, events that literally flipped the planet's orbit and sent it careening in the wrong direction. Then there are the ultra-hot Jupiters, an even more extreme category where temperatures exceed 3,600 degrees Fahrenheit. At these temperatures, molecules in the atmosphere break apart into individual atoms. Water vapor, which exists in the atmospheres of cooler gas giants, dissociates into hydrogen and oxygen. Even more exotic molecules like titanium oxide and vanadium oxide can form, creating atmospheric chemistry unlike anything we see on planets in our solar system. On planets like Kelt 9b, which holds the record as one of the hottest exoplanets ever discovered with dayside temperatures exceeding 7,800 degrees Fahrenheit, the conditions are so extreme that even atoms are being ripped apart. The planet is hot enough that iron exists as a gas in its atmosphere, and the intense ultraviolet radiation from its star is ionizing atoms, stripping electrons away and creating a plasma. In some sense, the atmosphere of Kelt 9b resembles the outer layers of a star more than it resembles a planetary atmosphere. These ultra-hot Jupiters are laboratories for studying matter under extreme conditions. They allow us to observe atmospheric processes that don't occur anywhere in our solar system, to study the behavior of elements and compounds at temperatures and pressures we can barely recreate in laboratory experiments on Earth. Every observation of these worlds adds to our understanding of how matter behaves when pushed to its limits. But perhaps the most philosophically intriguing aspect of hot Jupiters is what they tell us about the diversity of planetary systems. Before we discovered exoplanets, we had only one example to study our solar system. It was natural to assume that other planetary systems would look similar. Rocky planets close to the star, gas giants farther out, maybe some ice giants in the outer regions. The discovery of hot Jupiters shattered that assumption and revealed that planetary systems can be arranged in countless different configurations. This diversity has profound implications for the search for life. If planetary systems can be so dramatically different from our own, then Earth-like planets might be rarer than we hoped, or they might exist in configurations we haven't considered. Maybe life arises on moons orbiting hot Jupiters, or on planets in the habitable zones of systems that also contain hot Jupiters that migrated through and disrupted the inner system. The possibilities multiply with each new discovery, expanding our conception of where and how life might arise. Now let's turn our attention to a different kind of strangeness. not planets in extreme environments, but planets with bizarre compositions, worlds made of materials that seem to belong more in a jeweler's showcase than in a planetary system. Consider 55 Cancri e, a planet that's been nicknamed the Diamond Planet, for reasons that will become immediately clear. This world is roughly twice the size of Earth, but about 8 times more massive, making it what astronomers call a super-Earth. But it's not the size that makes 55 Cancri remarkable, it's what it's made of. Analysis of the planet's mass, radius, and the composition of its parent star suggests that 55 Cancri e might have a carbon-rich composition rather than the silicon-rich composition, typical of rocky planets, like Earth. Under the immense pressures inside the planet, this carbon wouldn't exist as graphite or amorphous carbon. Instead, it would be compressed into a crystalline form diamond. Scientists estimate that up to a third of the planet's mass could be pure diamond, a diamond the size of a planet, a world, where the mantle is composed of trillions upon trillions of carats of the hardest natural substance we know. The surface of 55 Cancri would be a hellscape, with temperatures reaching around 4,900 degrees Fahrenheit due to its close proximity to its star. Any carbon on the surface might exist as graphite, or even as a liquid carbon ocean, a sea of molten carbon lapping against shores of diamond. The very concept challenges our imagination. A world where what we consider the most precious gemstone is common as dirt, where diamond formations that would be priceless on Earth extend for thousands of miles in every direction. But the Diamond Planet raises fascinating questions about the diversity of planetary compositions in the universe. On Earth, and presumably on most rocky planets, silicon and oxygen are the dominant elements in the crust and mantle, forming silicate minerals and compounds. But if a planetary system forms from a molecular cloud that's enriched in carbon relative to oxygen, perhaps because it incorporated material from an ancient carbon star, then the resulting planets might have entirely different chemistries. On a carbon-rich planet, the minerals and compounds that form would be completely different from those we see on Earth. Instead of silicate rocks, you might have silicon carbide. Instead of water ice, you might have frozen hydrocarbons. The geology, if we can even call it that, would be alien in the most fundamental sense, built from a different chemical foundation than the rocky worlds we're familiar with. And 55 Cancri e might not be alone. We've identified several other exoplanets that could potentially have carbon-rich compositions. These worlds force us to expand our conception of what a rocky planet can be, to recognize that the familiar geology of Earth, Mars, and Venus might be just one possibility among many, that the universe contains rocky worlds built according to entirely different chemical rules. From diamond planets, let's journey to another compositional, extreme water worlds. Planets where the oceans are so deep that they might constitute the majority of the planet's mass. These aren't just planets with oceans, like Earth. These are worlds where water extends hundreds, or even thousands of miles deep, where the pressure at the bottom is so immense that the water transforms into exotic forms of ice that exist nowhere on Earth, naturally. GJ 1214b is one of the best candidates we've found for a true water world. This super-Earth orbits a small red dwarf star and has a mass about 8 times that of Earth, but it's much less dense than our planet. The low density suggests that a significant fraction of the planet must be composed of light materials, and water is the most likely candidate. Models suggest that GJ 1214b might have an ocean that extends from the surface down hundreds of miles, perhaps even thousands of miles, with no solid surface anywhere. As you descended through such an ocean, you'd pass through different layers, where the water exists in different states. Near the surface, it would be liquid water, perhaps superheated by the planet's proximity to its star. Deeper down, the increasing pressure would compress the water into exotic forms of ice. Yes, ice, but not the ice we're familiar with from our freezers. Under extreme pressures, water molecules arrange themselves into crystalline structures that are denser than liquid water, and that remain solid at temperatures far above water's normal freezing point. These exotic ices, designated by names like Ice 7, Ice X, and Icy 11, have properties that seem almost magical. They're hot ices, existing at temperatures of hundreds of degrees, yet remaining solid due to the immense pressure. Some forms can conduct electricity, something normal ice cannot do. Others have crystalline structures so compact that they're as dense as rock. In the depths of a water world like GJ1000, 214b, these exotic ices might form a solid core, a sphere of supercompressed ice surrounded by hundreds of miles of liquid water ocean, all beneath an atmosphere of steam and hydrogen. The conditions would be utterly alien, yet the basic chemistry, hydrogen and oxygen combined into H2O, would be the same as the water we drink every day. Water worlds raise intriguing possibilities for astrobiology. On Earth, water is the solvent of life, the medium in which biochemistry occurs. A planet with vast oceans would seem, at first glance, to be an ideal place for life to emerge. But there are complications. The sheer depth of these oceans might prevent any nutrients from cycling between the deep ocean and the upper layers where light from the star could provide energy. Without such cycling, without the geological activity that brings minerals up from the deep and cycles carbon through different reservoirs, could life get started? And then there's the question of what happens at the bottom of a water-world ocean. On Earth, the ocean floor is solid rock, and this interface between water and rock is where many important chemical reactions occur. Reactions that help maintain the chemical balance of the ocean. On a water world, if the ocean extends all the way down to a core of exotic ice, there might be no rock-water interface. The chemistry would be fundamentally different, and we can only speculate about whether such a world could support life. From the crushing depths of water worlds, let's ascend to atmospheres so massive and extended that they blur the boundary between planet and star, to worlds where the very concept of a surface becomes meaningless. These are the puffy planets, gas giants with densities so low that they would float in water if you could find an ocean large enough to test that hypothesis. WASP-17b holds a special place in the catalog of cosmic oddities. This planet is nearly twice the size of Jupiter, but has only half Jupiter's mass, giving it a density roughly 1/8 that of water. To put that in perspective, Styrofoam has a density about 15 times greater than WASP-17b. This planet is so diffuse, so insubstantial, that it represents an extreme we didn't think was physically possible when we first started studying exoplanets. What causes a planet to become so inflated, so puffed up, that it defies our conventional understanding of planetary structure? The answer lies in a combination of factors, starting with the planet's proximity to its star. WASP-17b orbits very close to its parent star, completing an orbit every 3.7 days, and the intense stellar radiation heats the planet's atmosphere to extreme temperatures. This heating alone would cause some expansion, but it's not sufficient to explain the planet's enormous size. Scientists believe that additional heating mechanisms must be at work. One possibility involves the tidal forces generated by the planet's orbit. If the orbit is slightly elliptical rather than perfectly circular, the gravitational pull from the star varies as the planet moves closer and farther away. This variation generates tidal flexing. The planet is literally being squeezed and stretched as it orbits. This flexing generates internal heat through friction, much like how bending a piece of metal back and forth makes it hot. This internal heat source, combined with the external heating from stellar radiation, could inflate the planet's atmosphere to the enormous proportions we observe. Another theory suggests that planets like WASP-17b might have cores that are less dense than we typically expect, or that their atmospheres contain elements that make them particularly susceptible to heating and expansion. Some models propose that these planets might have substantial amounts of titanium oxide or vanadium oxide in their upper atmospheres, compounds that can absorb stellar radiation very efficiently and convert it to heat, inflating the atmosphere like a hot air balloon. The existence of puffy planets forces us to reconsider the relationship between a planet's mass and its radius. In our solar system, there's a relatively predictable relationship. More massive planets are larger. Jupiter is more massive than Saturn and is also somewhat larger. But when we look at exoplanets, we find worlds that break this rule spectacularly. We find planets with Jupiter's mass but twice its size, and we find planets with twice Jupiter's mass but similar or even smaller sizes. The diversity is staggering, and it tells us that planetary structure depends on much more than just mass. It depends on composition, on heating, on orbital dynamics, on the history of how the planet formed and evolved. These puffy planets also raise questions about long-term stability. An atmosphere that's so extended and diffuse should be vulnerable to erosion by the stellar wind, the constant stream of charged particles flowing out from the star. Over millions or billions of years, this erosion could strip away significant portions of the atmosphere, potentially shrinking the planet and increasing its density. Or perhaps these planets are in a temporary state, a phase in their evolution that they'll eventually move past as they lose atmospheric mass and settle into more compact configurations. Now, having explored planets with bizarre compositions and structures, let's turn our attention to orbital mechanics, to planets whose paths through space are so eccentric, so extreme, that they experience seasonal variations that would make Earth's climate fluctuations seem trivial by comparison. HD 80606b has one of the most eccentric orbits of any known exoplanet. Its orbit is so elliptical that the planet's distance from its star varies by a factor of nearly 10 over the course of its 111-day year. At its closest approach, what astronomers call periastron, the planet skims just 3 million miles from the surface of its star, closer than Mercury is to our Sunday. At its farthest point apastron, it's nearly 30 million miles away, still closer than Earth is to the Sun, but a dramatic difference nonetheless. The consequences of this eccentric orbit are almost unimaginable. During the planet's closest approach, which lasts only about a day, the amount of stellar radiation hitting the planet increases by a factor of 800. 800. In the span of just a few hours, the planet's temperature skyrockets from around 900 degrees Fahrenheit to more than 2,200 degrees. This isn't a gradual seasonal change like we experience on Earth. This is a thermal shock, a sudden blast of heat that slams into the planet's atmosphere and drives massive, violent changes in atmospheric dynamics. Observations of HD 80606b during its periastron passage have detected enormous atmospheric disturbances. The sudden heating drives powerful shock waves through the atmosphere. Shock waves so intense that they can be detected from Earth as rapid changes in the planet's infrared emission. The atmosphere essentially explodes outward, expanding dramatically in response to the sudden influx of energy, then cooling and contracting as the planet moves away from its star and back out into the colder reaches of its orbit. What would it be like on such a world? Imagine an atmosphere in constant turmoil, with wind speeds that might reach thousands of miles per hour as air rushes from the dayside to the nightside, trying to redistribute the enormous amounts of heat deposited during periastron passage. Imagine storms so vast they could swallow Earth whole, vortices powered by temperature gradients that dwarf anything in our solar system. The Great Red Spot on Jupiter, that centuries-old storm larger than our entire planet, would seem almost tranquil compared to the atmospheric chaos of HD 80606b. The eccentric orbit of HD 80606b is almost certainly the result of gravitational interactions in the planet's past. Planets don't naturally form with such elliptical orbits. They form in circular or near-circular paths. Something must have perturbed this planet's orbit, likely a close encounter with another massive body, or a complex series of interactions, in a system that once contained multiple giant planets. The current orbit represents a snapshot of a dynamical history we can only partially reconstruct, a gravitational drama that played out over millions or billions of years. And HD 80606b isn't alone. We've discovered numerous exoplanets with highly eccentric orbits, each one telling a similar story of gravitational chaos and dynamical evolution. These planets give us insight into the violent processes that shape planetary systems, processes that might have occurred in our own solar system's early history, but left few traces we can detect today. Our solar system is relatively calm now, with planets in near-circular orbits that have been stable for billions of years. But it wasn't always this way. The early solar system was a far more chaotic place, with planets migrating, orbits shifting, and smaller bodies being scattered into the outer solar system or ejected entirely. From eccentric orbits, let's journey to another orbital extreme planets that orbit in planes dramatically tilted relative to their star's equator, or even completely perpendicular or retrograde. These misaligned planets challenge our understanding of how planetary systems form and evolve. In our solar system, all the major planets orbit roughly in the same plane, and that plane is closely aligned with the Sun's equator. This makes perfect sense given how planetary systems form. They coalesce from a disk of gas and dust that surrounds a young star, and that disk naturally lies in the star's equatorial plane. Planets that form from such a disk should inherit its orientation, resulting in a flat, aligned system, like the one we see around our Sunday. But many exoplanetary systems don't follow this rule. We've discovered hot Jupiters with orbits tilted at angles of 45 degrees, 90 degrees, even more than 90 degrees relative to their star's equator. Some planets orbit in a completely retrograde fashion, moving in the opposite direction from their star's rotation. These misalignments tell us that something dramatic must have happened to these systems after the planets formed, something violent enough to tilt entire planetary orbits away from their original orientations. The leading explanation involves gravitational interactions with other planets or with stellar companions in binary systems. In a process called Kozai-Lidov oscillation, a distant massive body can cause periodic variations in another object's orbital eccentricity and inclination. Over millions of years, these oscillations can pump a planet's orbit to extreme eccentricity, causing it to pass very close to its star. At that close approach, tidal forces from the star can circularize the orbit, but at a new, randomly oriented inclination. The result is a hot Jupiter with a highly misaligned orbit, a planet that ended up in a configuration completely different from where it started. These misaligned systems provide some of the strongest evidence we have for the chaotic and violent history of planetary system evolution. They show us that the orderly, peaceful arrangement we see in our solar system is not the universal norm, that many, perhaps most planetary systems, went through periods of gravitational upheaval that reshuffled their planets and created the bizarre configurations we observe today. Now, let's explore another category of cosmic oddity: planets that exist in resonances, locked in gravitational dances, where their orbital periods relate to each other through simple mathematical ratios. While orbital resonances aren't necessarily bizarre in themselves, several moons and planets in our solar system are in resonances. Some exoplanetary systems display resonance chains so precise and so complex that they represent cosmic clockwork of extraordinary intricacy. The TRAPPIST-1 system is perhaps the most famous example. This system contains 7 Earth-sized planets orbiting an ultra-cool dwarf star, and remarkably, the inner 6 planets are locked in a chain of orbital resonances. The orbital periods relate to each other through ratios like 8:5, 5:3, 3:2, and 4:3. This means that for every 8 orbits the innermost planet completes, the next planet out completes exactly 5 orbits. For every 5 orbits of the second planet, the third completes 3, and so on down the chain. This resonance chain is extraordinarily stable and extraordinarily precise. The planets are locked together in a gravitational embrace that has likely persisted for billions of years, each planet's gravity tugging on the others in a perfectly synchronized pattern that reinforces the resonant configuration. It's like a cosmic musical chord, where each planet contributes a note, and the resulting harmony is mathematically perfect. But here's what makes this even more remarkable. Resonance chains like the one in TRAPPIST-1 are extremely difficult to achieve through random chance. If you randomly place 7 planets around a star, the probability that they would naturally end up in such a precise resonance chain is effectively 0. The existence of this configuration tells us that the planets must have migrated into their current positions, moving through the protoplanetary disk in the system's youth and being captured into resonances as they moved. This process of resonant capture during migration is now understood to be a common feature of planetary system formation, but TRAPPIST-1 takes it to an extreme. The precision of the resonances in this system suggests that the planets migrated smoothly and slowly, avoiding the gravitational chaos that characterizes many other systems. It's a snapshot of orderly planetary migration, a system that evolved through gentle gravitational nudging rather than violent interactions. The resonances also have practical implications for the planets themselves. When planets are in resonance, they experience periodic gravitational tugs from their neighbors that can maintain orbital eccentricity and generate tidal heating. For the TRAPPIST-1 planets, this tidal heating could be significant enough to affect their internal structure and potentially maintain subsurface oceans on some of the worlds. It's a reminder that orbital dynamics and planetary habitability are intimately connected, that the arrangement of planets in a system can directly influence whether any of those planets can support life. From the precise clockwork of resonant systems, let's turn to a different kind of strangeness. Planets that are so old, they challenge our understanding of when planets could first form in the universe's history. These are the ancient worlds, planets that formed when the universe was a mere fraction of its current age, in an era when the cosmos was a very different place. PSR B1620-26b, sometimes called Methuselah after the biblical figure known for his extreme longevity, is estimated to be approximately 12.7 billion years old. To put that in perspective, the universe itself is only about 13.8 billion years old. This planet formed when the universe was less than 1 billion years old, in an era when the first generation of stars was just beginning to enrich the cosmos with heavy elements. This ancient age creates a puzzle. The very first stars in the universe, what astronomers call population 3 stars, contained almost no elements heavier than hydrogen and helium. All the carbon, oxygen, silicon, iron, and other elements that make up planets had to be manufactured inside stars through nuclear fusion and then dispersed into space through supernovae. This process takes time, and early models suggested that planets couldn't form until the universe had been enriched with sufficient heavy elements, perhaps after several generations of stars had lived and died. But PSR B1600 and 20-26b proves that planets can form even with very low metallicity, even when heavy elements are scarce. This has profound implications for the prevalence of planets in the universe. If planets could form in the early universe, then they've been around for most of cosmic history. Life, in turn, could have emerged on planets billions of years before Earth even existed. There might be civilizations in the universe that had already risen and fallen before our solar system was born, cultures that flourished for eons in a younger, different cosmos. The planet itself has had a remarkable history. It currently orbits a binary system consisting of a pulsar and a white dwarf, stellar remnants that are themselves ancient. The planet somehow survived not one but 2 stellar death events first, when one star in the original binary system swelled into a red giant and then collapsed into a white dwarf, and later when the other star exploded as a supernova and became a pulsar. The fact that the planet survived both of these cataclysms and remains in orbit around the stellar remnants is extraordinary, a testament to the resilience of planetary bodies and the complexity of orbital dynamics in evolving stellar systems. From ancient planets that have witnessed billions of years of cosmic history, let's turn our attention to worlds that are bizarre, not because of their age, but because of their sheer physical impossibility. According to our initial models, planets that are too large, too massive, or too dense to fit comfortably into our classification schemes. Consider the case of super-Earths and mini-Neptunes, categories of planets that don't exist at all in our solar system, but appear to be among the most common types of planets in the galaxy. These worlds occupy the gap between Earth, the largest rocky planet in our solar system, and Neptune, the smallest ice giant. Our solar system jumps from planets with masses around 1 Earth mass directly to planets with masses around 15 Earth masses or more. There's nothing in between. But when we look at other planetary systems, we find this gap filled with a diverse population of planets ranging from about 2 to 10 Earth masses. What are these planets made of? Are they rocky super-Earths, scaled-up versions of our own planet, with thicker crusts and more massive cores? Or are they mini-Neptunes, smaller versions of ice giants with thick hydrogen and helium atmospheres surrounding rocky or icy cores? The answer, frustratingly, is that we often can't tell. A planet with 5 Earth masses could be a dense, rocky world or a less dense world with a substantial atmosphere. And from our current observational capabilities, these two scenarios can be difficult to distinguish. Some super-Earths exhibit properties that seem to defy explanation. Take TOI 849b, a planet roughly 40 times the mass of Earth, but with a radius only 3.4 times Earth's radius. This gives the planet a density that suggests it's composed almost entirely of rock and metal with little to no atmosphere. But here's the puzzle. A planet this massive should have been able to capture and retain a thick atmosphere of hydrogen and helium during its formation. The fact that it apparently hasn't suggests that something stripped away the atmosphere. Perhaps the planet formed as a gas giant and then lost its gaseous envelope through some catastrophic process, leaving behind only the dense core. TOI 849b might be what astronomers call a Chthonian planet, the exposed core of a former gas giant that lost its atmosphere to stellar winds and intense radiation. If this interpretation is correct, then TOI 849b gives us a unique window into the interiors of gas giants, allowing us to study directly what lies beneath the thick atmospheres of Jupiter and Saturn. It's like finding a fossil, a remnant of a planetary type that no longer fully exists, but whose remains tell us about a past we couldn't otherwise access. Then there are planets at the opposite extreme worlds, so massive that they approach the boundary between planet and brown dwarf. Brown dwarfs are often called failed stars, objects that formed like stars but never accumulated enough mass to sustain hydrogen fusion in their cores. The dividing line between the most massive planets and the least massive brown dwarfs is fuzzy and contested, but it's generally placed around 13 Jupiter masses, the mass at which deuterium fusion can begin. Some objects straddle this boundary, leaving astronomers to argue about whether they should be classified as planets or brown dwarfs. Dennis P. J082303 124912001b, mercifully often shortened to just 2M0746 plus 20b, has a mass approximately 29 times that of Jupiter, well into brown dwarf territory. Yet it orbits a star, formed in a protoplanetary disk, and shares many characteristics with massive planets. Should we call it a planet? A brown dwarf? Does the distinction even matter? Or is it just an arbitrary line we've drawn in a continuum of objects that nature sees no reason to categorize? These boundary cases force us to confront the limitations of our classification schemes. We like to put objects into neat categories: planet, brown dwarf, star. But the universe doesn't care about our categories. It produces a continuous spectrum of objects with a continuous range of properties, and sometimes we encounter objects that fall right on the boundaries we've drawn, forcing us to question whether those boundaries are meaningful or merely convenient fictions. From questions of planetary mass and composition, let's journey to planets whose atmospheric compositions are so exotic that they challenge our understanding of atmospheric chemistry. These are worlds where it rains glass, where the sky is red, where clouds are made of molten rock or vaporized metals. HD 189733b is a deep blue planet, a color that might sound appealing until you learn why it's blue. Unlike Earth, where the blue color comes from the scattering of sunlight by nitrogen and oxygen molecules in the atmosphere, HD 189733. 3B's blue hue is caused by the scattering of light by silicate particles, essentially tiny particles of glass suspended in the atmosphere. And it's not just glass particles floating peacefully in the sky. The wind speeds on HD 189733b can reach up to 5,400 miles per hour, more than 7 times the speed of sound on Earth. At these velocities, those silicate particles become deadly projectiles. It rains glass sideways on HD 189733b, driven by winds so fierce they would shred anything in their path. The temperature exceeds 1,700 degrees Fahrenheit, hot enough to melt rock. The planet is tidally locked, with one side perpetually facing its star and the other in eternal darkness, creating a permanent temperature gradient that drives the horrific winds as the atmosphere tries to transport heat from the day side to the night side. The atmospheric dynamics of such a planet are almost impossible to visualize. On Earth, our most powerful hurricanes have wind speeds around 200 miles per hour, and they cause catastrophic damage. Imagine winds more than 25 times faster than that, carrying particles of molten glass, sweeping across a landscape where the rocks themselves might be melting. It's a vision of hell rendered in science rather than mythology, a real place in the universe where the conditions are so extreme that they mock our everyday experience. But HD 189733b is far from the only planet with exotic atmospheric phenomena. On other hot Jupiters, scientists have detected evidence of titanium oxide and vanadium oxide in the atmosphere, the same compounds used in industrial processes on Earth, but existing as gases in the scorching atmospheres of these alien worlds. These compounds can absorb stellar radiation and create temperature inversions, atmospheric layers where temperature increases with altitude rather than decreasing, the opposite of what we see on Earth. Some planets might have clouds of corundum aluminum oxide, the mineral that forms rubies and sapphires. On these worlds, it could literally rain gemstones, with crystals of ruby and sapphire forming in the upper atmosphere and falling through layers of progressively hotter gas before vaporizing at lower altitudes. The very concept seems fantastical, more at home in a fantasy novel than in a scientific description, yet the chemistry and physics support such exotic possibilities. On cooler planets, we might find clouds of water ice or ammonia ice, more familiar to us from our studies of the outer solar system. But even these more normal clouds can behave in bizarre ways on planets with atmospheres very different from those in our solar system. Some models suggest that on certain planets, layers of different cloud types might stack vertically, with water clouds at one altitude, ammonia clouds above them, and perhaps clouds of other compounds higher still, creating a stratified atmosphere where each layer has its own distinct properties and chemistry. Now, as we near the end of our journey through the cosmic cabinet of curiosities, let's consider one final category of bizarre worlds, planets that are actively disappearing, evaporating away before our eyes in real time, leaving behind trails of gas that stretch for millions of miles. Kick 1, 2, 5, 5, 7, 5, 4, 8. B is one of the strangest objects we've ever detected. It's not just evaporating, it's disintegrating. The planet orbits extremely close to its star, completing a full orbit every 15 hours. And it's so hot that its rocky surface is literally boiling away. The evaporating material forms a comet-like tail of dust and gas that streams behind the planet as it orbits. And this tail is so substantial that it causes the star's brightness to vary in irregular ways, as different amounts of material pass in front of the star during each orbit. What makes Kick 1255754 even more remarkable is that the planet itself appears to be shrinking. Observations over multiple years have detected variations in the transit depth and shape that suggest the planet is losing mass at different rates over time, perhaps due to variations in stellar activity or changes in the planet's surface composition, as different layers are exposed and vaporized. This planet gives us a glimpse into a death spiral, a world in the final stages of its existence. Eventually, perhaps in a few million years, or perhaps sooner, there will be nothing left but a diffuse cloud of rock vapor and metal atoms, a ghostly remnant of what was once a planet. And even that cloud will eventually dissipate, dispersed by stellar winds and radiation until no trace remains. But Kick 1255754 isn't dying alone. We've discovered several other planets in similar states of disintegration, worlds caught in the act of evaporating, each one adding to our understanding of how planets can die. These observations are valuable because they show us processes that occur over timescales too long for us to observe in their entirety, but which we can catch glimpses of by finding planets at different stages of the same evolutionary path. The study of disintegrating planets also connects to broader questions about planetary system evolution and the ultimate fate of planets. What happens to a planetary system over billions and billions of years? Do all close-in planets eventually spiral into their stars and disintegrate? Or do some reach a stable configuration where they can survive indefinitely? What role does stellar evolution play as stars age and change? How do their planets respond? These questions bring us full circle to where we began, contemplating the sheer diversity and strangeness of planetary systems throughout the universe. Every planet we've discussed, from Korat 7b, with its raining rocks, to the diamond world of 55 Cancri E, from the ancient Methuselah planet to the blue hell of HD 1897333b, represents a data point in our growing understanding of how diverse planetary systems can be. And here's what's truly humbling. Despite the thousands of exoplanets we've discovered, we've barely scratched the surface. Our current detection methods are biased towards certain types of planets, large planets close to their stars. Planets that are easy to detect because they block a lot of starlight or cause their stars to wobble noticeably. The planets we found are, in a sense, the low-hanging fruit, the easiest targets for our current technology. As our observational capabilities improve, as we launch more sophisticated telescopes and develop more sensitive detection techniques, we'll undoubtedly discover planets even stranger than the ones we've discussed. There are almost certainly categories of planets we haven't imagined yet, worlds with properties so bizarre that we currently lack the conceptual framework to even predict their existence. Consider what we couldn't have predicted before the exoplanet era began. We couldn't have predicted hot Jupiters. Our theories of planet formation said gas giants should only exist far from their stars. We couldn't have predicted super-Earths and mini-Neptunes. Our solar system contains no examples of these planet types. We couldn't have predicted the sheer diversity of orbital configurations, the misaligned systems, the highly eccentric orbits, the planets orbiting binary stars and pulsars. Each unexpected discovery forced us to revise our theories, to expand our understanding of what's possible. And there's no reason to think we've reached the end of that process. The universe has surprised us repeatedly, and it will surely continue to do so. The bizarre exoplanets we've explored today serve another purpose beyond just satisfying our curiosity about the cosmos. They provide natural laboratories for studying physics and chemistry under extreme conditions we could never reproduce on Earth. They test our theories of planetary formation and evolution, forcing us to refine and improve our models. They expand the known parameter space of planetary properties, showing us the full range of what's possible when you have billions upon billions of planetary systems forming and evolving over billions upon billions of years. And perhaps most importantly, these strange worlds recalibrate our expectations about our place in the universe. For centuries, we assumed our solar system was typical, that other planetary systems would look like ours. The discovery of exoplanets has thoroughly demolished that assumption. Our solar system is not typical. It's just one possibility among countless others, one arrangement of planets among the infinite variations that nature can produce. This realization has profound implications for the search for life beyond Earth. We can no longer assume that life requires a planetary system like ours. Maybe life can emerge in places we never considered on moons of hot Jupiters, in the subsurface oceans of rogue planets, in environments so alien we struggle to recognize them as potentially habitable. The diversity of planets suggests the possibility of an equal diversity of life, biology, adapted to conditions we can barely imagine. Organisms that would seem as impossible to us as these bizarre planets once seemed. As we look to the future, new telescopes and missions promise to reveal even more about these distant worlds. The James Webb Space Telescope is already analyzing the atmospheres of exoplanets in unprecedented detail, detecting molecules and compounds that tell us about atmospheric chemistry and dynamics. Future missions will be able to directly image exoplanets, to study their surfaces and atmospheres without the planets being backlit by their stars. We'll be able to search for biosignatures, chemical indicators of life, in the atmospheres of worlds light years away. And with each new discovery, our sense of the cosmos will expand. We'll find more bizarre planets, more exotic worlds, more variations on the theme of planetary existence. We'll continue to be surprised, to be amazed, to have our expectations overturned by the creativity of nature. The bizarre exoplanets we've discovered, the worlds of raining rock and diamond cores, of glass-filled winds and comet-like tails, to of ancient origins and imminent doom. These are more than just scientific curiosities. They're reminders of how vast and varied the universe truly is, how much we have yet to learn, and how our tiny corner of the cosmos is just one of countless variations on the theme of planetary systems. As we continue to explore, to observe, to analyze these distant worlds, we're engaging in one of humanity's oldest and most profound endeavors, the quest to understand our place in the universe. Every bizarre planet we discover, every unexpected property we detect, every assumption we're forced to revise, brings us one step closer to answering the fundamental questions that have driven human curiosity since we first looked up at the stars and wondered what might be out there. The universe is stranger than we imagined, stranger than we can imagine. And the bizarre exoplanets scattered throughout the galaxy are the proof. They exist in states of matter we didn't know were possible, in orbital configurations that shouldn't be stable, with compositions that defy our expectations, under conditions that mock our theories. They are testaments to the infinite creativity of physics and chemistry, operating across billions of years and trillions of miles of space. And somewhere out there, orbiting stars we haven't yet observed, are planets even stranger still worlds waiting to be discovered, waiting to surprise us, waiting to force us once again to expand our understanding of what's possible in this endlessly fascinating universe we call home.